I know that it's lunchtime in Italy, but let's. So it's pleasure to have Nicola Bellomo from Padova, and he's going to talk about gravitational wave science in the SKAO era. I'll send you a reminder when 5 minutes are left.
Yeah, sure. So let me try to, okay, I'm less in. So, hello. Well, for those who don't know me, like I'm Nicola, and I'm currently a postdoc at the University of Padua. Today, I would like to talk about which kind of science we can hope to achieve with the SKAO observatory. Thank you very much for the invitation. Please stop me if you have any question at any moment. So first of all, let me start describing like this observatory. SKA is actually about to start, well, is under construction, and after probably decades of planning is very ready to start to take in data in the next couple of years. The observatory is has around 9 members, official members, and many other like are applying to join in. So the observatory is going to be split into two parts. One part is going to be in Australia, and the other one in South Africa. So let's discuss first the Australia part. The Australia part is going to target radio frequency in the range from 50 to 300 megahertz, and is mainly done by dipole antennas. So in the background, what you can see is like an artistic rendering, but actually, like since the construction is ongoing, I'm able to show you, okay. Yes, this is the actual deployment of the antenna radial arrays. So every bunch that you can see is made by around 200 antennas that works as a single one. And what it's going to do is going to perform interferometry. And here you can have an idea. Like the second part of the observatory instead is going to target the frequency between 350 megahertz and 15 gigahertz. Is going to be based in South Africa and is going to be a different kind of instrument. As before, we are in the scenario where we started deploying antennas. Here you can see like the lift of the dishes and the actual deployment on top of the towers. So in terms of construction timeline, we are at the AA05 stage. Hope you can see my arrow, like which has been currently completed, and we are starting to move forward the so-called AA star configuration. The AA star is the last stage that has been fully funded. And it's going to be mark the time where we're going to start taking data and start doing some science verification. The goal, of course, is what is called AA4, which is the full baseline, which has more or less twice the number of antenna, both in the South Africa and Australia part. But is not fully funded yet. So for the goal of like motivating why we should actually like invest into like the final design sensitivity, the community has first done a book about the science cases that can be brought forward with SKA, and it was this advanced astrophysics with the square kilometer array. The book has been published 10 years ago, and many things have actually changed in the past 10 years. So we came back together, and we are currently drafting the second version of the book, which is going to call Advanced Astrophysics Second, which is going to comment on all the novelties that have been understood in the past 10 years. This is very relevant, for instance, in the case of gravitational waves, since in 2014, we really there were no gravitational waves. So as a like further motivation of this, I'm also along with Philippa Cole, like the co-chair of the new gravitational wave, the gravitational wave working group. And right now, I'll present some of the science chapters that you're gonna be able to find in the book in the future. So like results will not be completed because the chapters are like being drafted, let's say right now. But by the end of the year, you're gonna be able to find it publicly. So let me start from what I already anticipated before, which is the drastic change that happened in the past 10 years. And in particular for gravitational waves, we had two major observations. Like the first one, like in 2015 and following from there onward, is the detection of gravitational waves in the Earth's kilohertz band. Right now, that is already well-established branch of science with hundreds, if not more, events currently detected, which brought also significantly novelties in the understanding of stellar evolution. The second large novelty was the detection of a gravitational wave background in 2023 by multiple collaboration. In general, let's say the group of all this collaboration ends up in the big umbrella of the International Pulsing and Timing Array, and their detection was in the nanohertz band, which is gonna also be like the band where SKAO is gonna be sensitive. So let me comment a bit of how SKO is gonna contribute. And the way it's gonna do it is just by discovering and targeting more millisecond pulsars. So like we know that in our galaxies, there are multiple millisecond pulsars. These provide an ideal candidate to detect gravitational waves in the nanohertz band because they are characterized by a very stable period. So we are able to monitor like their period with a very precise accuracy. So far, like we are following up around 67, 70 pulsars with the International Pulsar and Timing collaboration, but SKO is gonna bring many more into the game. So the general idea is that for each one of these pulsars, we detect like the emitted pulse, and we detect it over the span of many years. And once we have detected this like signal, we can start building a timing model. A timing model is like a model that is gonna give us an idea of when to expect the next pulse in this series. And what we can compute is like the shift between the measured time of arrival between these pulses compared to the expect one. And by theory, we know that this is proportional to the gravitational wave amplitude. Like this has been the task that has been performed over like decades. Like and finally, like 2 years ago, we reached like a sufficient confidence level to claim that we have detect a common spectrum and spatially correlated process that is compatible with a gravitational wave background. So in this scenario, like I would like to emphasize the two parts, the common spectrum and spatially correlated. And these parts are connected with like the shape of the spectrum in the frequency domain, and the fact that this spectrum is depends on the pulsar positions through what is known as Helling-Dance curve. So regarding on the first part, here on you can see like basically the amplitude of the background as a function of the frequency. And you can see that the classical violin plots represents the uncertainty in the measure. And you can see that our measure is actually compatible with power law spectrum with exponent 13/3. This exponent is like the predicted one by imagining that this background is sourced by inspiraling supermassive black holes. So this was a strong confirmation of what we do actually expect. However, like the most probably most important part is the detection of a Helling-Stone curve, which is the curve that I am showing in the right plot. This curve is a function just of the separation of pulsars and is characteristic of the passage of gravitational waves. No other effect that is currently known is able to reproduce this curve. So this was really like the key ingredient missing from the previous data release. Now that we are equipped with this sort of like a detection, we can start asking ourselves like, okay, what could generate? And as I already told you, like the main candidate was inspiring supermassive black hole mergers. Well, inspiring supermassive black holes. These objects are typically formed as a result of galaxy mergers, but the dynamics that goes into such a process is quite involved. So as an example, let me point out to some of the ingredients that enters in the modeling of the signal that for instance, nanograv uses. So first of all, you need to characterize your population of galaxies and the likability that these galaxies merge. Then you have to populate these galaxies, each one of them with supermassive black holes of a given mass. Observationally, we know that the mass of the supermassive black holes and the stellar mass of the bulge are actually correlated, but that's one of the key ingredients. And then you have to introduce some mechanism that after the merger of galaxies is strong enough to bring the supermassive black hole closer, let's say below parsec distance. And from that point onward, gravitational wave emission is affecting in driving forward the mergers. Of course, also details of the kind of orbits of the binary enter in the picture. But as you can already see from this very simplified and mostly phenomenological set of steps, there are many assumptions in the process. And when we actually compare data in green with the outcome of the simulation based on the model on the left, we can see that it appears there is some mild tension between the theoretical predictions and our measurements. This has opened the door to alternatives to supermassive black holes. And here in this plot, I don't plan to enter in the details of all the different models listed on the x-axis, but it seems that many alternatives are strongly preferred to the basic supermassive black hole explanation, with a bias factor of let's say order 10 or more. So it's it appears is a quite significant preference. However, we have to be really careful in interpreting these stronger preference, in the sense that if we start with a model that doesn't fit well the data, of course, any model with a bunch of free parameters that can be tuned to reproduce the data is going to perform better. But that doesn't mean that the original model was just meant to be tossed away. It just means that we have to refine it and until when we can drop many of the assumptions done in the process, or at least compare them with other observation, and be sure that you are actually implementing the right baseline model. And I think SKAO is gonna be a key player in this effort. So as my personal take, let me say that what I find really interesting about this instrument is its capability of probing different aspects of the cosmos in a very complementary way. And it is precisely using these synergies between, for instance, emitted electromagnetic radiation and emitted gravitational wave radiation that we might be able to shine light on a set of astrophysical processes that now are, let's say, not known very well. And actually, these sort of synergy are represented by the very large numbers of a working group that are currently exist in SKAO, which I show here on the left. At the moment, there are 14 working groups, and their science ranges from let's say habitable planets to cosmology and a very high energy process in astrophysics. So in the following, I'll comment about just a small selection of science cases. And I'll avoid mentioning, but in the slides here on the top right corner, you're going to find the name of the people working on these projects, and also the relevant papers that these authors have published. So in general, these science cases have just been shown to poke at different aspects of physics. I provide a full list at the end. So let me start from the first case. So as we said, it seems that astrophysical sources are not enough to explain the strength of the detected signal. And one alternative is to study whether gravitational waves produced in the early universe can actually complement the astrophysical signal to justify what we observe. So so far we have a probe that inflationary pictures is extremely successful in providing a mechanism that creates curvature perturbations that later it produces the set of observation we are very familiar with as the cosmic microwave background radiations, or to plant the seeds of what are going to become the large structure of the universe. However, we could not yet probe the existence of primordial gravitational waves, and this is one of the goals of future cosmological observation, especially because the gravitational waves are a sort of smoking gun of inflation, since you cannot avoid the production of gravitational waves in the inflationary scenario, even though their amplitude can be really small. So far we have just upper limit on the scalar to tensor ratio, and hopefully the situation is going to improve in the future. However, in the realm of gravitational waves, we don't need to resort just to direct production. There are also indirect production mechanisms. In this case, scalar-induced gravitational waves. In fact, if we write down the gravitational wave propagation, we found out that scalar perturbation, here indicated by phi, can actually be a source of tensor perturbation. Now, at cosmological scales where scalar perturbations are really small, of order 10 to the minus 5, that's not really an effective mechanism. But in other ranges of scales, in particular at small scales, we could be in a different situation. So CMB already rules out this sort of, this has been a relevant mechanism. But if we open like the spectrum to other scales, in particular small scales that are not currently constrained by CMB, we see that we can even hope to have fluctuation of order unity, or conversely, power spectrum of order 10 to the minus 2, and which might be even desirable for other purposes, for instance, to provide the primordial black holes, if we find it an attractive dark matter candidate. And this sort of perturbation necessarily generates a gravitational wave background of scalar-induced gravitational waves that could be targeted both with PTA or with future interferometry like SKA. So just like a quick reminder, what do we care about this? Well, first of all, yes.
Can I ask a question?
Yes.
So in this slide, there is this QSO, which is much better than SKA.
So, okay, yeah. So yes, so that constraint comes from a paper claiming that you can observe, I think it was like a lensing of quasars emission lines. So when we wrote our paper where this picture is taken from, we introduced this constraint just let's say for the sake of completeness. But that's there's it has been very debated. Let's leave it at that. So I would take this constraint with like a grain of salt. In case you want to learn more, the paper of my student Alba Kalaya contains the reference to the original paper. It's, I mean, I personally do not trust the procedure through which they obtain these constraints, but that's
So the grain of salt is how many orders of magnitude? No,
I don't think that the procedure holds, so like I would not I would just discard it.
Okay, thank you.
So as I was commenting, like maybe like you want a PBH as a dark matter candidate. So I think everyone is up to speed, but let me briefly comment what the PBH are. PBH are black holes that are formed in the radiation-dominated era, at least before Big Bang nucleosynthesis, to avoid the disturbing observation that we have about that. For PBH that have not evaporated yet, we have just a limited range of mass that is allowed, and is more or less between 10 to the minus 17 and 10 to the 4. Larger black holes would have formed during or after BBN, so they incur in other kind of problems. And at the current day, there are potential dark matter candidates, even like constraints on their abundance are plenty debated. The interesting thing is the process is so extreme, the process of black hole formation via the collapse of like big chunks, big fluctuations in the early universe is so extreme that even if we require that only, let's say, a single primordial black hole exists in the universe, that would require the power spectrum to be, let's say, around 10 to the minus 3, where this blue bar is. So even if primordial black holes are just a subdominant component of dark matter, incredibly subdominant, the fact that they are generated through these very large scalar perturbation would create enough tensor perturbation to be detected with future detectors. And not only that, because like if now we are interested in the shape of the spectrum that is produced by these scalar-induced perturbations, well, we find out that the shape is actually very sensitive to the dynamics happening during inflation. And what the authors have shown up is that if, for instance, the shape is very sensitive to the presence of primordial non-Gaussianity. And in the papers referenced above, like you're gonna find like example of different kind of non-Gaussianity and the different effect they have on the shape of the spectrum. So hopefully with SKA, we can measure the shape of the spectrum and potentially provide constraints on dynamics along the inflation. The second science case I would like to tell you is the use of PTA as a test of general relativity. And in particular, I'm considering the polarization degrees of freedom. So in GR, we know that electromagnetic waves are characterized by, gravitational waves are characterized by 2 degrees of freedom corresponding to 2 polarization tensor. However, in GR extension, the total degrees of freedoms ramps up to 6, where we had 2 additional scalar and 2 additional vector modes. We of course know GR is very well tested in multiple regimes, but like it's always good like to try to confirm it. And the particularity of these extra degrees of freedom is that they produce a Hellingsdown curve that is significantly different from the one produced by the E plus E cross. So in this plot, you can see like the standard tensor term Hellingsdown in is the one I'm pointing at. And then you can see like both like the scalar, I think is dark red, and then you can see the vector in blue and the scalar in green. Of course, like a real measurement of the total Hellingsdown is gonna be some, let's say, balance between these, since every polarization degrees of freedom is gonna contribute with a given amount. However, this shows the potential of probing the existence of extra degrees of freedom just through PTA measurement. So the way to do it is actually to do a harmonic analysis in which like the Hellingsdowns is expanding into Legendre multiples and then constrain the size of these multiples. Because let's say the value of these multiples is going to be radically different whether like we have scalar, vector, or tensor degrees of freedom. And the procedure has been already shown to be very successful with PTA data. Here I'm showing like a paper performing this analysis on real data. And you can see that like this analysis is matches up with the regular PTA analysis in gray, and is able to measure the same amplitude, let's say compatible exponent, and the values of C2. That is the main, the largest coefficient in the case of tensor modes. Apart from testing general relativity, we can use PTA also as a test of dark matter candidates. We already talked about fundamental black holes, but the story doesn't end up there. In this case, I'm considering ultralight dark matter particles. And I'm considering those because this kind of dark matter candidate has always been invoked apart in, let's say, generalization of standard models, but also as solution of known problems in astrophysics. One of them being the core versus cusp problem, which is like the observations of structures that appear to have a dark matter profile that is not compatible with a Navarro-Franken-White, typical of cold dark matter particles. Now, like the resolution of this sort of discrepancy between our theory and observation, might be multiple. However, it turns out that introducing axion, or let's say ultralight axion-like particles with masses of around 10 minus 23 electron volts helps in solving this problem. The reason is that the Brownian wavelength of such a particle is of order of the kiloparsec, which is precisely like the size of the core of structure where we observe like a flattening of the dark matter potential. However, the presence of these let's say state of this dark matter candidate triggers also other effects. And one of them is the generation of time-dependent pressure that provokes the time changing in the gravitational potential of our structure. And these time changing are compatible with those of gravitational waves of, let's say, in the range of nanohertz if the mass of the particle is of 10 to minus 22, 23 electron volt. Also, as a coincidence, for reasonable values of masses and let's say densities of these particles, we have that the strength of this sort of fake gravitational wave signal is comparable with those of supermassive black hole binaries. Sorry, I thought there was something else. So how do we distinguish this from a true gravitational wave? Well, first of all, this sort of effect will not show up a Helling send-down curve, but we can also reverse the argument and say, okay, what if we don't detect this extra effect generated by fuzzy dark matter? Well, in that case, we can put constraints on the abundance of dark matter that is actually contained in our galaxy. And what future forecasts showed is that with let's say even let's say decades of SKAO in data, we're going to be able to constrain the amount of fuzzy dark matter in our galaxy to the, let's say, percent to per mil level. Let's now switch gear into something totally unexpected, in the sense that we have observed gravitational waves in the Earth's kilohertz band. We have a plan detector, LISA, that is going to cover the millihertz band, and we observe gravitational waves in the nanohertz band. So it seems that we are totally insensitive to the microhertz band. And in fact, this band is currently not covered by any experiment, and even, let's say, tentative experiment and this mu-RS proposal looks quite futuristic, in the sense that to build an interferometer that is able to target this frequency range needs the arm of the interferometer to be of, let's say, millions, hundreds of millions of kilometers instead of just a million of kilometers. So you could think of a potential detector able to cover this frequency and be on a Martian orbit. However, there might be an indirect way to probe this frequency range. And in particular, these authors have suggested that we can monitor pulsars in binaries because in particular that motion, because the presence of a gravitational wave background induces like a secular change in the properties of binary orbits. And the pulsar in this respect are extremely useful because we can time them extremely precisely. Thus, we can know the evolution of the orbit extremely precisely. And in particular, like they found out that targeting binary millisecond pulsar with periods from hours to years, we might be able to cover like the missing gap in the gravitational wave spectrum. Okay, I think, okay, I think I have 10 minutes, right? So let me move to the, okay, I'll be quick. So that's great. Like I show you like many science cases, but they have a common thing. They all like are kind of insensitive of whether these gravitational waves are produced by astrophysical sources or cosmological. So now we would like to ask ourselves, okay, can we break this intrinsic degeneracy? Because otherwise everything is fair game. Now, how to do that? Well, one possibility could be anisotropies of the stochastic gravitational wave background. This is because depending on whether like so the sources are astrophysical or cosmological, the anisotropy could be dramatically different. So let me point out that there is actually a hierarchy of anisotropies, and so the on top of the, so if you imagine like a isotropic background, the first kind of anisotropy we would observe would be the one given by so-called loud sources. With loud sources, we mean supermassive black hole binaries that are really nearby. So these provide an anisotropy of, let's say, 1 part in 10 to 100. And these anisotropies are only there if astrophysical sources are the key ingredients of the detected background. Moving down in the level of anisotropies, we have kinetic anisotropies that contributes, let's say, to 1 part in 1,000. This sort of anisotropies is common to both cosmological and astrophysical sources, and because they're just due to our relative motions with respect to the rest frame. And as for instance, we observe kinetic anisotropies in the CMB. Then moving down the ladder, we have intrinsic astrophysical anisotropies, which are, let's say, around 1 part in 10 to the 4, 10 to the 5. These anisotropies are anisotropies due to the fact that the core of our background is going to be produced by the superposition of many supermassive black hole binaries, all of which basically trace structure formation. And finally, of course, this is going to be present only in the astro scenario. And finally, we have intrinsic cosmological anisotropies, which are way smaller. Like in any case, here you should imagine numbers as ballparks. These are part of 1 in 8 to 1 part in 10 to the 8, 10 to the 9. But they're still there, so it's important to mention them. So in the following, maybe I'll present the kinetic anisotropies, but just let me comment beforehand. We had some work on astrophysical anisotropies, and it turns out that with SKA, you can really hope to target and possibly detect them if they're present. So why do we care about kinetic anisotropies? Well, like in current observation, apart from the very famous H0 tension, that is basically tension due to the different measurements in the value of H0 or on the inference on each node, we have a different sort of tension, which is the dipole tension. So we already know like that the motion of us, let's say us observer, is induces a dipole in any observation. We measure it quite accurately from the cosmic microwave background. Overall, like it corresponds to us moving at a velocity of around 370 kilometers compared to the background. And apart from the velocity, we also measure the direction. So this counts as a early time measurement of our dipole. What about the late time? Well, in the case of late time, we can use larger structure, which could be like galaxies in different wavelengths or the radio background, to infer a second time the value of our dipole. And what happens in this case is that the value we find does not correspond to the value we find with the CMB. So, and the direction is not compatible. So for instance, here you see where the CMB dipole is and where like its likely position inferred by large-scale structure is. Absolutely not compatible. This is also common to multiple large-scale structures. So you can do with galaxy, radio background, quasars, all return a dipole that is, let's say, shifted down in the left in these coordinates. Apart from the position, you can also see that the amplitude is way larger. So here, let's say a factor 10, so 1 order of magnitude larger. So here you see what's the value for the CMB and where is the measured values, for instance, with quasars. Now, there's no reason why that should the case. So what can we do to resolve this issue?
2 minutes, 2 minutes left.
So one issue, one way to move forward is add an independent probe as like a gravitational wave background. So in fact, like if you write the first order correction of the Hellingsdown curve, we find it's proportional to our velocity through this beta factor. So by measuring to high accuracy the Hellingsdown, we're able to infer what's the value of the dipole. And current forecast show us that this is actually feasible with SKAO data. Let me skip that and just mention that the cases doesn't end here. There are other possible sources of dipoles that are currently investigated, as well as a synergy with other astrophysical probes or other gravitational wave detectors in our frequency bands. And I'll leave my conclusion up here. I hope I show you like what's the potential of SKAO is. And I think it's a really exciting time also to think about a new way to explore or to test